All right. Now, we've used the Pythagorean identity before when we were calculating the lengths of sides. Um, a squared plus b squared equals c squared type of thing. But these Pythagorean identities also exist with trig functions. So let me correct something here. Okay, so what we have here is we have this geometric construction, which I've shown you before, but now I've added a few more things. So here, we know that we've got a right triangle inscribed in a unit circle. And we know that this right triangle, this is the cosine of our angle of interest. This is the sine of our angle of interest. And this is the tangent of our angle of interest. Again, the lengths of these line segments are actually equal to those values. Okay. And so as the angle of interest changes, the geometry of the lengths of each of these sides changes correspondingly. Okay. But what I've added to this are the other three trig functions, which are the reciprocals. Okay, so notice that we've got cosine theta, and what's the reciprocal of cosine? It is secant. The secant is this value, is the length of this line segment, the entire line segment AD. So let me do AD like that. Okay, and then we have sine, and the reciprocal of sine is cosecant, which is the length of that line segment. And notice where the termination of these reciprocals are. The termination of secant is where that tangent line intersects the x-axis, and the termination for cosecant is where that tangent line intersects the y-axis. And the length of this segment is tangent theta, and the reciprocal is the other part of the tangent line. That's the cotangent. So all of these values change as the angle of interest changes. And the lengths of each of these truly represent the changing of the values of the trig functions and their reciprocals. Now, what's interesting about just looking at this geometric construction of all of these trigonometry ratios all in one place is this helps you see all the different trig identities that there are. So let's, take a step back really quick and look at what the Pythagorean theorem is, right? So if you take the two sides adjacent to the right angle and you square them and you sum them, that will be equal to the square of the hypotenuse. It's equal to the square of the hypotenuse. So anywhere that you find a 90-degree angle, you can take the square of the two sides adjacent to the 90-degree angle, and that'll be equal to the square of the side opposite the right angle. Well, when we look at this geometric construction, we've got a right angle right here. And adjacent to the right angle, we've got sine and cosine. So when we've got triangle ABC, we have cosine squared, okay, which is this side adjacent to the 90-degree angle, plus sine squared theta, which is this side adjacent to the 90-degree angle, and that should be equal to the hypotenuse squared. And in a unit circle, the hypotenuse is 1, and 1 squared is just 1. So just by looking at this picture, this geometric construction of these trig functions, we can see right away, here's what's called the Pythagorean identity for trig functions. Now it's useful to take this Pythagorean relationship and kind of rearrange it, right? So if we subtract both sides by sine squared theta, okay, these will add up to 0, and you're left with cosine squared theta equals 1 minus sine squared theta. So that Pythagorean identity can come in useful sometimes. And if instead of subtracting sine squared from both sides, and you instead subtract cosine squared from both sides, then you end up with this one. So from this one Pythagorean identity, you can kind of manipulate it to get these two alternate versions of it, which may end up helping you. Okay, so I'm trying to, I want to select all this. Okay, now, in person, I would tell you guys, quickly, don't look down below, just fold the page up and cover the bottom 4 lines here. Okay. And the reason why I want you to cover those bottom 4 lines is looking at this picture, do you see any more Pythagorean identities? Do you see any other right triangles? Okay, well, one such right triangle would be triangle A, B, D. And right here is the right angle. So it should be tangent squared theta plus 1 squared theta equals secant squared theta, right? The two sides adjacent to the 90-degree angle should be equal to the square of the opposite side to the 90-degree angle. And if we come down here, you can see this is one of our trig identities. And you can manipulate it just like we did with the previous one. All right. So let's look for another one. Let's delete that so we don't get confused. Another one is we've got A, B, and E. There's another right triangle. And you can see the right angle is already drawn in. So we should have cotangent squared theta plus 1 squared theta equals cosine or cosecant squared theta. And if we come down here, you can see we've got cotangent squared theta plus 1 squared equals cosecant squared theta. Okay, that's one. And let's see here, another one. We've got triangle ADE. So A, D, and E. So here is our right angle. Oops. Here's our right angle. So we're going to have secant squared theta plus cosecant squared theta is equal to cotangent theta plus tangent theta squared. So if we come down here, that's what we have. Secant squared theta plus cosecant squared theta is equal to tangent theta plus cotangent theta squared. Okay, and let's look for one more trig identity. And that is in triangle BCD. So BCD, that one right there. So you can see we've got our 90-degree angle. Okay, so this one is interesting. So we're going to have sine squared theta. That's pretty simple. But how do we get this line segment? Well, that's going to be secant minus cosine and all of that squared. And then that'll be equal to tangent squared. So let's come down. Yep. Okay, there should be a square right there. I'm missing it. So sine squared theta is equal to secant minus cosine theta squared, and that's equal to tangent squared theta. And if you were to multiply all this out, it would simplify to this. But I wanted to put it in this way, unsimplified, just so you could correlate it to this picture up above. So, I'll be honest with you. When I first took trig, and I was shown these different trig identities, they didn't make any sense to me. I just saw them on a sheet, memorized them, learned to use them. It would have helped me a lot to have seen this picture, where I could just draw in right triangles and I could see, oh, this squared plus this squared equals this one squared. That would have gone a long way to help me understand why those identities are the way that they are. Okay, so I'm going to make that little correction here, but you don't need to see me do that. Let me know if you have any questions.